Where we have some strength contribution from the concrete itself. Here we have a picture of a shear wall showing some of the steel is going on. So we have horizontal steel and vertical steel helping toward the shear.
Next we have section 11.6, design of walls for in-plane shear forces. So first of all, 11.6.1, it says the critical section for shear is either 0.5 times the length of the wall or 0.5 times the height of the wall, which is less. So we'll be taking it, say, the shear strength maybe this point here, and this is the min of 0.5 height of the wall or 0.5 length of the wall. But either way, we'll get in to find the strength. So say if we've got 500 kilonewton load here, which is significant from perhaps the stability. So first of all, we have thigh VU equals thigh times the contribution from the concrete itself, which is VUC, plus thigh VUS, which is from the steel, in this case, most likely the mesh. And bear in mind that the max is VUC, which equals 0.2 F-C times 0.8 times the length of the wall times thickness of the wall. So let's say we've got a 1 meter wall by 200. So the maximum capacity we have is 0.2, and again we've got 50 MPa concrete, 2 times 50 MPa concrete times 0.8 times the length of the wall, which is 1000, times the 200 thick wall. And what we end up is 1600 kilonewtons. Okay, so that's our first check. We know we can move on to the next here. So second part now, what we're going to find is the strength contribution from the concrete. And you can find that in part 11.6.3, which is the shear strength excluding wall reinforcement. In our case, we have the height on the wall divided by the length on the wall being 3 divided by 1 meter, so that equals 3. So therefore we are part B. So then part B is VUC equals 0.05 times square root of the strength of concrete plus 0.1 divided by so plug our numbers in. What we end up with is 0.05 times square root of 50 plus 0.1 square root of 50 divided by the height of the wall. So in this equation, sorry, the parenthesis is around here. So we have square root of 50 times 0.1 divided by 2, which is 0.35. And then plus 0.05 times square root of 50, 0.35. Again. And so we add that together, 0.8 times 200 times 1000, which is for the length. And what we end up getting is 113 kilonewtons. Next, we have the shear strength contribution from the wall reinforcement. So that's 11.6.4 is VUS equals reinforcement ratio times as we said before, thickness of the wall 200, length of the wall 1000. and yield strength steel, 500 MPa. And we have here the reinforcement ratio. So if you look at 11.7.1, in the vertical direction, it is at least 1.5%, in the horizontal direction, at least 2.5%. So in our case, it is the lesser of the two, so it'll be 1.5%. So what we end up with is 0.015 times 500 times 0.8 times the length of the wall times thickness of the wall. And what we end up with is 0.015 times 500 times 0.8 times 1000, 200. And what we end up with is 1200 kilonewtons. So, as we said before, VU equals VUC plus VUS, and in our case is 113 kilonewtons plus 1200. So we're getting quite a lot of help from the steel. So what we end up with is 13 kilonewtons, greater than the original 500. So therefore, we're good to go and we're bloody okay.